Okay, this is section 2.1. We're looking at introduction to functions today. And you'll want to make sure you watch the entire video, take some notes. You can stop and start and rewind as much as you need to get all the notes completed. And at the end of this video, there will be a quiz. Be sure you complete the quiz the same day you would normally have class. Okay, so functions. What is a function? Well, function is a set of ordered pairs, and in that set, no two pairs have the same first coordinate with different second coordinates. So a very easy way to think of this is the same x cannot be paired with two different y values. So if we have, let's say, for instance, 4 as our x value, 4 can only be paired with one y value. So the first thing you're going to be doing to determine is something a function or does it define a function is looking at the points they're giving you in your ordered pairs. So here's our first set. We've got several different ones here. And if you notice, we've got 2 points here, 3, 4, and 3, 6. They have the same x coordinates with different y coordinates. That does not meet the definition of a function. So because of that, we would say this is not a function. All right, our second example down here for B, if you look at this. Now, what you really need to look for is to see, first off, do any x values repeat? If no x values repeat, then that's all you need to check for. It will be a function. And you can see here, none of our x values repeat in this group. Now we have a 5 and a -5, but those are different values. So nothing is repeated here. So because of that, we can say, yes, this is a function. All right, now these will be multiple choice questions on WebAssign. You will only have 2 options. Yes, it is a function, or no, it is not a function. If you recall, when we discussed that earlier in the semester, I said those types of multiple choice only give you one opportunity to try and answer correctly. So be sure you're checking your points carefully and determining yes or no, and then choosing the correct option. Okay, our third example here is a linear function. We've just recently done some graphing with this. This is a function, and the way you can tell is when you're looking at your equation, it must have a y value. Okay, so as long as there is a y value in your equation, then your linear equation is a function. It could be something like what we see here. It could be as simple as y equals 3x. Or it could even be something like y equals 4. As long as the y variable is part of the equation, it is a function. If there's no y value and it's just x, then it is not a function. One of the other tests you have is when you are given a graph and you're trying to determine is the graph a function, and this is called the vertical line test. So we are going to draw a vertical line across the sketch of these functions, and if it intersects at more than one point, then it is not a function. So a graph is a function if and only if no vertical line intersects at more than one point. So let's take a look at the ones here that are functions. So this first one is a function. This one down here is a function. All of these on the bottom row are functions. You can see if I put a vertical line here, and no matter where I move the vertical line, it is only going to intersect one point. This one here is also a function. However, these other 3, there are many places where I can put a vertical line and it will intersect more than one point. In fact, this last one is a vertical line and it intersects every point. So for these 3, we would say, no, this is not a function. So again, the vertical line test is a quick, easy way to check if a graph represents a function. All right, so we're going to be looking into function notation and actually evaluating some functions. So the difference here is we've taken the y equals from our equation and we replaced it with this notation here. The way we would read that is f of x equals. So f of x, or the function of x, means we're going to evaluate our function for whatever values of x we have. Now, f is not always the letter you're going to see for a function. Usually, it's going to be f, g, sometimes h, maybe even k, depending on how many functions you're looking at in a particular problem or a particular situation. So when we're evaluating these, basically we're going to substitute values. And then simplify. Sometimes simplify means we're going to get a single value or a single number. Sometimes simplifying just means simplify the terms as much as possible because we may have variables. All right, let's take a look at this first one. So here's our function, f of x equals x squared plus 3. And we're going to evaluate it first for f of -2. That means wherever there is a variable, we're going to put -2 in place. So this is going to equal -2, that entire amount squared, plus 3. So -2 squared is +4, plus 3 gives us 7. So f of -2 equals 7. The second one is f of 2a. So we're plugging 2a in place of x. So f of 2a is going to give us 2a, that entire amount squared, plus 3. Now, when you square this or raise it to the power of 2, you have to raise the 2 to the power of 2 and the a to the power of 2. So 2 squared is 4, and then a to the power of 2 is just a squared, and then we still have a plus 3. So there's our value when we find f of 2a. So one thing to remember, if you're plugging in or substituting a variable into your function, then your answer will still contain a variable. We don't know what that variable a equals, so it's just going to be a variable in our answer. All right, our last one is f of b plus 2. So we're substituting b plus 2 in place of x. That means we have b plus 2 squared plus 2. So b plus 2 squared, remember, to square something or raise to the power of 2, you multiply that entire amount times itself. So it's b plus 2 times b plus 2. To simplify that, you would want to use the FOIL method. We're multiplying b times b, and then b times 2, and then 2 times b, and then 2 times 2. So we get b squared plus 2b plus 2b again, plus 4, and then we still have a plus 2 out here. And then finally, again, we want to simplify this, so we're combining our like terms together. So we're going to end up with b squared plus 4b plus 6. Okay, so that is evaluating the function. Again, we're plugging in the given values that we have into our function. All right, the next thing with functions that's important to understand is the domain of a function. So the domain represents the first coordinates. Domain is always your x values. But we want to know what x values define the function. And define means we want to get a real number solution. No imaginary values. So anything that would give us an imaginary value or any value that's not a real number, we would exclude from our domain. And we're going to list this in interval notation. So remember, interval notation, which we use with our inequalities, shows a range of numbers. So we want to know what is the range of numbers, or what is the set of numbers that will work for our function. Okay. Now, if there's no exclusions, which we will have in a few cases, then our range is all real numbers. And the way we're going to write that is -infinity to +infinity. So this would be our domain if there are no restrictions. Okay, so here's our examples. Now, the first one here, we have a linear function. We know it's a linear function because there's no fractions or exponents or radicals or anything else and there's just a single variable. All linear functions, as long as it is written in function notation, have a domain of negative infinity to positive infinity. So this one has a domain of all real numbers. Again, make sure you're writing these in interval notation. Okay, our other two examples, you can see one's a fraction, the other one has some radicals. And if you look up here at the top, you probably want to add this to your notes, very important. A variable in the denominator or in the radical will limit the domain. So those are the two main things we're looking for. Is there a variable in the denominator, if there's a fraction, or in the radical, if we have a radical? Those things will limit the domain. Okay, for a fraction, our denominator cannot equal 0. Dividing by 0 is undefined. So that would give us an undefined value for our function. Okay, for our second example, we have a fraction, and hopefully you're aware that the denominator in a fraction cannot equal 0. So that would give us an undefined value and give us an undefined value for our function. So we need to figure out what would make our denominator 0, and that's the number or numbers we have to remove from the domain. Now, if you see it right away, that's great, but if you don't, you can always say, well, I'll take the denominator and let it equal 0. And let's solve for x. To do that, we would add 2. So when x equals 2, we get 0. So that's the number we need to remove from the domain. So that means we can have all the numbers less than 2. That would be negative infinity up to 2 with a parenthesis, and then anything greater than 2, from 2 to positive infinity. And between it is where you would put your union symbol. So this is what your domain is going to look like anytime you have a fraction and you're removing one number, whatever that number is, that makes your denominator 0. And notice these are all parentheses. Okay, for our radicals, so notice over here, I've added a little note. Radical uses only non-negative numbers, meaning we can take the square root of 0, or we can take the square root of a positive number, but not a negative number. So that means what is inside the radical, in this case it's x minus 4, has to be greater than or equal to 0. Well, once again, we can solve our inequality. This time we can just simply do it by adding 4 to both sides. So we get x is greater than or equal to 4. And how do we write that? Well, we're going to use interval notation. That would be 4 to infinity with a bracket this time, since it is also equal to 4. Now, you notice we have two different functions here for this example. So we are only concerned with what is inside the radical. What is underneath our radical cannot be a negative value. So as long as x is 4 or greater, for this one here, we get a non-negative value. For this one over here, we would also get a non-negative value. So the 3x, the minus 5, has no effect on our domain, and we're not going to worry about those. So both of these functions have the exact same domain of all values greater than or equal to 4. So when you're doing a domain for a radical, ignore anything outside of the radical. You're only concerned with what is inside your radical. The last thing we have with functions for now is graphing functions. And the nice thing about that is we've already done it. We're going to graph our functions just like we graph equations. So you can use an XY table. You can graph with intercepts. We're also going to have some absolute value functions, like example B on your paper. So just like we did before, we can choose some values for X, plug them into the function, and solve for Y to get our points. Or if you want to use intercepts, you could do that. So let's take a look at these. So we've got 3x minus 1 is our function. So that means if we let x equal negative 2, 0, and 2. So again, remember, y represents f of x. So if we plug our values in and get f of x, that's going to be the y values on our graph. All right, when x equals negative 2, we get negative 2 times 3 is negative 6, minus 1 is negative 7. When x equals 0, we get 0 minus 1, which is -1. And when x is positive 2, 2 times 3 is 6, minus 1 is 5. So -1, -7, sorry, -2, -7, 0, -1, and 2, 5. So here is the graph of this function. For example B, we have an absolute value function. So remember, we want to find the vertex first, and that's going to be the point 1, -2. Remember, for H, we want the opposite value or the opposite sign. For K, we're going to use the same sign. So 1, -2 is right there. There's our vertex. And again, we're going to pick two numbers, one to the left and one to the right. I'm going to use -1 and 3. So if we plug in -1, -1 minus 1 is -2. The absolute value of -2 is +2. Minus 2 is 0. If we plug in 3, 3 minus 1 is 2. Absolute value of that is 2. 2 minus 2 is 0. So we have 3, 0. And we have -1, 0. And remember, you're going to use array tool in WebAssign. One going to the right and one going to the left. And there's our absolute value graph. So once more, these graphs are just like graphing the graphs you did in the last section. Be sure you know how to graph a line and how to graph an absolute value. There will be one of each of these graphs on your test for Unit 1. Make sure you can graph them both correctly. Okay, the last thing we're going to look at is function behavior. So we're looking at how a function behaves on the graph. And there's three possibilities. The function can be increasing, decreasing, or constant. So if a function is increasing functions are going to go up, or they will rise as we move from left to right on our graph. Decreasing functions, as you probably already guessed, are going to go down, or the graph will fall as we move from left to right. And then finally, a constant function. Well, a constant function remains the same. An easy way to think of that is it's going to be a flat line. Okay. So we're going to list all of these again in interval notation based on the x coordinates. Make sure you're paying attention and you're listing your intervals as the x values. So again, we're always moving from left to right on our graph. Okay, here's our example. So starting on the far left, we start over here and we move to the right. Our function is going down. So it is decreasing, and it continues to decrease all the way till we get to this point right here. So that decreasing amount starts all the way on the far left, which is -infinity, and it continues all the way until we reach the point where x equals 0. So from -infinity to 0, our graph is decreasing. From that point, the graph starts to move up, or is increasing. It continues to increase till we get to this point right here. Again, we're looking for the x coordinate of that point. That is 4. So from 0 to 4, our graph is increasing. Again, notice these all have parentheses. I'll explain why that is in just a moment. And then finally, from 4 all the way to the rest of the graph, we're going to assume it continues in the same direction, which again will take us to positive infinity. So from 4 to infinity, our graph is constant. Now, why do we use parentheses for all of these? Well, at each one of these points, these are called points of inflection. This is where the graph is changing direction. So it's not increasing or decreasing or constant. It's actually changing at that point. That's why we don't include 0 and 4 in our intervals for decreasing, increasing, or constant. Okay, now you will not always have all three of these on your problems. You may have a graph that is decreasing and then it remains constant the rest of the time. Or maybe it increases and then it decreases and it's never constant. So pay attention to the direction of the WebAssign. It will tell you what to enter if one of these does not exist. Okay, finally, the last thing we have is your quiz question. So be sure to submit this. You should be submitting it the day you have class. You do not need to do the attendance because you're not actually attending class. So be sure and submit your quiz question. Notice it says watch the signs. This is a distance question, so be sure and watch your signs carefully. And remember, with distance, if you do not get a perfect square that will give you a whole number, then you're just going to leave your answer in radical form. Okay, that's it. Again, you can go back and review and watch and rewind as many times as you need to. We will see you in class next time, and be sure to finish up your homework. If you haven't finished any homework assignments that are due, be sure to email me or use the Ask Your Teacher button if you have any questions on either homework or any other questions about class.